Welcome to Ask and Learn.
In this video, we are asked to show that the set of security class with the lexicographic each relation defined like this is a lattice. So the relation here is just like a different version of lexicographic, just because each entry in a pair is from a different set. So the first entry is just positive integers, but the second one is actually a set of finite elements. And so on the second entry, instead of the lesser than or equal to sign that we are used to, is just become being a subset. Okay, everything else is just the same. So this proof want us to show that it is lattice. First, we have to show that it is a poset, and you probably can intuitively tell that it is a poset because both sides that we use to compare each entries are themselves partial ordering, so there shouldn't be anything complicated there. So reflexive, obvious, everything relate to itself. Anti-symmetry, I will just say that since both less than or equal to and being a subset are anti-symmetric, so you can prove it using this property. So if you write it out, it's gonna be anti-symmetric. I will just skip that. Transitive as well, so both less than or equal to and being a subset are transitive. So when we prove, we just write each entry out and they're gonna relate to each other in the end. Okay, what's interesting would be on the lattice side of proof. So let's go over the definition. It would be a lattice if any set of two elements from S is, so write it like this: A1 C1 A2 C2 has the greatest lower bound and least upper bound. So the proof is just that you can find the actual bound for both lower bound and upper bound from the element given, because the relation are quite simple, right? It's less than or equal to and being a subset. And when you find it, you just claim that, okay, it is least upper bound, greatest lower bound, and show that it is like the case. So I will show the least upper bound. Okay, so we have first entry is max between the two, and second entry is the union between the two. All right, if we have another element, call it A3 C3, okay, that is an upper bound of that set. So A3 must be greater than or equal to A1 and A2, right? And so A3 can be lower than max of the two, because max here is just choose one element that is greater. If A3 is less than one of them, then this condition will break. So this can happen. All right. Also C3 must be such that I should write C1 is inside C3 and C2 is inside C3, right? For this to be an upper bound, the second entry has to be larger than C1 and C3. And now it means C1 union C2 is a subset of C3 as well. Why? If this is not the case, there will be some element in the union that is not in C3, right? But that element must be in either C1 or C2, and it's gonna break one of the two condition above here. So that can happen. So we have this relation. And so in the end, we have an upper bound. We see that it is greater than or equal to this element that we claim to be least upper bound. And so we have proven that it is in fact least upper bound because any other upper bound can be lower than that. Okay? The proof for greatest lower bound is the same, like very similar. So you can do that yourself. We are done with this. I think yes. Okay, that is it